There are many important reasons for studying asteroids like the target of Osiris-Rex asteroid Bennu. First and foremost, for me especially, they're geologic remnants from the dawn of our solar system. They're literally the first material that formed around our star, and they represent the building blocks of planets, and we hope, in the case of Bennu, of life, and the reason that Earth may be a habitable planet in the form of delivering water and other important volatile material.
When we look at asteroids, which are these primitive objects, these little leftover pieces from solar system formation, and we find they may have organics, then that tells us perhaps the conditions for life could have erupted anywhere in the solar system and Earth was just right.
When we study meteorites, we think they represent these asteroids and their different histories, but they've all interacted with the Earth's atmosphere, its biosphere, its hydrosphere, and so we don't know what effect just interacting with the Earth has had on these meteorites. We really want to get samples that are pristine, and so we can do all of those things through this mission.
Osiris-Rex is a mission in the NASA New Frontiers program. Our objective is to travel out to a near-Earth asteroid named Bennu, survey that object in great detail to understand its geology, its mineralogy and composition, ultimately select a single location on the asteroid surface to acquire a sample and return that material back to the Earth for scientific analysis.
Asteroid Bennu is a fragment of the early solar system, an unmelted, unaltered piece of the origin of the solar system. It preserved the ingredients, the raw materials that went into the formation of planets, the formation of life. By bringing a sample back to the Earth, such as Osiris-Rex will do with samples of Bennu in 2023, we'll be able to look at the samples in laboratories around the world to understand in great detail the nature of the sample and its place in the origin of the solar system.
The Osiris-Rex spacecraft launched in 2016, and it's actually taken us 2 years to get to the asteroid Bennu. And in that time, we had an Earth flyby, so we used an Earth flyby in 2017 to change the plane of our orbit to match Bennu's orbit plane. And it's also provided a great opportunity from a flight dynamics perspective to really calibrate our models and learn how to fly the spacecraft, which will help us in the really challenging part of the mission, which is orbiting in the low gravity environment of the asteroid. Over the past few months, the flight dynamics team has been getting images of the asteroid Bennu, and it started out as just a very small point source in the camera, and it's been getting bigger and bigger and bigger in the field of view. And that's allowed us to perform optical navigation to refine our prediction of the asteroid's orbit and allow us to more precisely navigate and target our approach to the asteroid.
As Osiris-Rex approaches the asteroid, we've done a series of braking maneuvers called asteroid approach maneuvers to slow down the spacecraft so that we can get into orbit around the asteroid later this year. We're also taking lots of images of Bennu to understand its rotation, look for natural satellites, and potential dust plumes.
This is an extremely exciting time on Osiris-Rex as we're just poised at arrival at Bennu. And one of the most exciting things to us, and relieving too to the engineers, is how closely the asteroid has resembled what we had predicted. Early on, our science team, prior to launch, had come up with a model of what they thought the asteroid would look like based purely on ground-based radar observations from Arecibo. And from that, they created a reference asteroid that we used as the requirements to design the mission against. But no one could be sure that the asteroid would really look like the scientists had predicted. So it's been a tremendous relief to us to find that the actual Bennu is very similar to what the scientists had predicted. So the science team really nailed it.
Right now, as we're approaching asteroid Bennu, we're looking for debris or other objects that are orbiting the asteroid, just in case we need to avoid those. And then once we arrive on December 3rd, we'll perform preliminary survey. And in preliminary survey, we fly over the North Pole, South Pole, and the middle of the asteroid. This helps us to map the gravity of the asteroid and understand how to operate near such a small body. Additionally, this will be the first time that we get close-up pictures of the surface, and we'll know how smooth or rocky the surface that we're going to study is.
As we get closer to asteroid Bennu, we'll begin to map its surface in higher detail. What we'll be able to do is first identify the distribution of rocks and particles that might pose a hazard to the sampling mechanism on the spacecraft. And we'll also get a better sense of what the shape of Bennu is like at smaller scales. Looking at Bennu in more and more detail is going to help us identify all the areas that we shouldn't go to grab a sample from.
Throughout 2019, we'll be doing global characterization of the asteroid, basically making maps of the entire surface, We're interested in its topography. Are there craters? Where are the boulders, the valleys, the mountains of the asteroid? And then we want to understand the distribution of geologic materials. Are we finding different patches of minerals in one location versus another? And why are certain areas have a composition and others may be different? We're going to be looking, most importantly, for areas where we can collect a sample.
Osiris-Rex will collect a sample from Bennu using our TAG-SAM, which is the Touch and Go Sample Acquisition Mechanism. What that is an arm connected to this sampler head that you see here. This is similar in size to an air filter from a car. How this mechanism works is there's compressed gas that is released that will stir up the regolith from Bennu, store it into this canister, which we will then put inside of our sample release capsule and bring back to Earth. We will collect the sample of Bennu in 2020 and return it to Earth in 2023.
Once we're in the vicinity of our home world, about 4.5 hours before impacting the top of the atmosphere, the spacecraft spins up and releases that sample return capsule. The spacecraft fires its engines to perform a deflection burn, going off into orbit around the sun, and the return capsule enters the Earth's atmosphere, targeting a landing in the Utah desert. I'll be there on site when we open that capsule up and we see those samples for the first time, and science begins at that point on the next phase of the mission, the sample analysis period.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called Osiris-Rex to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
From a distance, everything in our solar system appears to be in its place. However, if you take a closer look, sometimes you can find asteroids, like Bennu, leaving their home in the inner asteroid belt and passing very close to Earth. Most other asteroids tend to stay grouped together in a few regions of our solar system, yet some still end up in our backyard. So once these asteroids get close, what makes the difference between a near miss and a potential hit? NASA's Osiris-Rex mission will help better answer this question when it visits Bennu, but scientists think that a force called the Yarkovsky Effect might be an important part of the answer. So how does this effect work? Well, like Earth, most asteroids rotate slowly as they move through space. During the day, the surface of the asteroid is illuminated by the sun, so it absorbs heat and grows warmer. During the night, however, the surface cools down, emitting the heat it absorbed as radiation. This radiation exerts a force on the asteroid, acting as a sort of mini-thruster that can slowly change the asteroid's direction over time. On larger asteroids, this doesn't amount to much, but on small ones, it can make a pretty large change over time. Because the surface emits the most heat radiation at the end of the day, the direction the asteroid rotates can ultimately determine what happens in the long run. Other factors, such as composition, asteroid shape, and surface features, can modify the magnitude and direction of the Yarkovsky thrust. By studying the Yarkovsky effect on Bennu with the Osiris-Rex spacecraft, NASA scientists hope to better predict how an asteroid might move through the solar system, and whether it poses any danger to us here on Earth. So the next time an asteroid starts gradually moving into our neighborhood, we'll have a better idea of exactly where it'll end up.
NASA is sending the Osiris-Rex spacecraft to explore near-Earth asteroid Bennu. To carry out its mission, Osiris-Rex is equipped with a suite of remote sensing instruments, including a spectrometer called OVIRS.
Osiris-Rex is a mission to bring a sample back from an asteroid. That's not something that we've done before, and that's very exciting.
The idea behind Osiris-Rex is to go to a pristine building block of the solar system to try to find out more about how they formed and to bring a sample back here to Earth.
Osiris-Rex's primary science goal is to grab a sample of asteroid Bennu and return it to Earth for analysis.
Planetary scientists are interested in asteroids because they're chemistry sets representing the formation of the solar system. You can't learn that on Earth because the Earth has erosion and other processes that have changed its pristine condition.
Asteroid Bennu is interesting because it's one of the blackest objects in the solar system, so we think it's covered with carbon material, organics, the building blocks of life.
To search for organics on Bennu, a team at NASA's Goddard Space Flight Center built the Osiris-Rex Visible and Infrared Spectrometer, or OVIRS.
OVIRS is a spectrometer. What that means is it breaks down light into a lot of little individual wavelength packets. When you look at very fine detail from spectra, you can tell what the material is that you're looking at, and that's what we're excited about. The idea of going out and looking at something and saying, oh, I know what that's made of, and that would be a good place to take a sample.
Before arriving at asteroid Bennu, OVIRS will have to survive 2 years in the unforgiving conditions of space. Fixing a broken part after launch is not an option, so OVIRS has a uniquely durable design.
OVIRS is a very simple instrument. It has 2 mirrors and no moving parts. And the reason we like that kind of design is because moving parts are one of the things we worry about breaking in space. And once it breaks, your instrument is lost.
The instrument has to operate in a very harsh environment. There's no air in space, there's a high vacuum, things can heat up. Well, if you can eliminate moving parts, that's just one more risk that you don't have to worry about. I don't have to worry about, oh, is that shutter open or closed, or is that motor moving? So we very specifically try to get rid of things that can fail, and fail in a bad way.
Designing instruments to survive in space is critical, but just getting there can be a bumpy ride. Rockets shake their payloads during launch, so instruments like OVIRS must pass a vibration test to prove that they are launch-worthy.
It is the test that I hate the most in the world. You've spent 5 years making this nice little beautiful thing, and you hand it to somebody and say, try to break it.
So one of the things we do in vibration testing is we'll shake it as hard as we think it's going to see, plus a little bit more, in every possible direction, just to make sure nothing is going to break off during launch.
On OVIRS, we actually had a case where the glue came a bit apart during thermal testing, and then when we put it on the vibration chamber, a full assembly gave way and there was a big pulse on the instrument. We had to stop and go back and make sure that everything was fine, which it was. We also had to redesign things a little bit, and that shows you the value of testing. Had that been on the launch chamber, we wouldn't have been able to do anything about it.
Osiris-Rex is a cutting-edge mission to explore asteroid Bennu and the origins of our solar system, and OVIRS is critical to the mission's success.
Osiris-Rex is just such an interesting mission. The concept of going to one of these really primitive bodies and bringing back a sample that we can then study here in the Earth is pretty spectacular when you think about it. From the OVIRS instrument itself, I'm actually quite excited to see if we can see organics on the surface and what interesting minerals we actually do find, because we won't know that until we get there.
We've got a very good instrument complement on top of a mission that's taking a sample. So we can tell what we're taking samples of, we understand the context of the sample that's returned, and the sample, when it comes back, will be analyzed by people all over the world for the next 40 years. So it's just this very nice, complete package.
The Osiris-Rex spacecraft was launched with a clear mission: collect a sample from an asteroid called Bennu and send it back to Earth. But with the number of known asteroids in our solar system reaching into the hundreds of thousands, why was Bennu chosen? What made it the best target? The first set of selection criteria was proximity to Earth. The most accessible asteroids are located around 74 to 153 million miles away. And in that group, the most ideal targets are ones with an Earth-like circular orbit and a low degree of tilt due to spacecraft maneuverability. At the time of selection in 2008, that brought the number of known near-Earth objects down from 7,000 to 192. From there, the size of the asteroid became a factor. Bigger meant better in this case, because asteroids with smaller diameters rotate faster, and material on their surface are more easily ejected. Not ideal conditions for safely grabbing a sample. So, mission scientists wanted the target to have a diameter larger than 200 meters. That brought the candidates down from 192 to 26. The chemical composition of the asteroid was the next factor, because we want our return sample to help us learn more about the history of our solar system and life on Earth. That dropped our target list to 12 asteroids with a known composition. And from there, only 5 of those were ideal for sampling because they are known from Earth observations to be carbon-rich. This matters because a carbon-rich asteroid may contain organic molecules, volatiles, and amino acids that may have been the precursors to life on Earth. So, Now it's decision time. Of these 5 contenders, why Bennu? Quite simply, it's because there was more information about it available to scientists. It was the only object of the 5 that had been observed with radar. This provided not just an accurate measurement of its size, dimensions, and shape, but also suggested it has a smooth surface with an ample amount of material to sample, and few large boulders to get in the way. We didn't have this level of detail with the others, which put the ability to safely get a surface sample in doubt. Sorry, fellas. The material we gather from asteroid Bennu will help generations of scientists better understand how the planet's formed and the source of the organic materials and water that help spawn life on Earth. And beyond learning about the past, studying Bennu can help us plan for the future. Everything from space travel to utilizing natural resources and better understanding the risks of asteroids. And this is why we chose Bennu.
Osiris-Rex is a NASA mission to explore near-Earth asteroid Bennu, a remnant from the dawn of the solar system, and to return a sample of Bennu to Earth. On September 8, 2016, Osiris-Rex began its journey to Bennu from Cape Canaveral, Florida, aboard an Atlas V rocket. It lifted off shortly before sunset, climbing eastward over the Atlantic Ocean to traverse the night side of Earth. 1 hour later, Osiris-Rex separated from its Centaur upper stage rocket and drifted into space. It deployed its solar arrays to catch the rising sun and made a final pass over Australia before embarking on its outbound cruise to Bennu. After a year in orbit around the sun, Osiris-Rex briefly returned to Earth in September 2017 for a gravity assist. The spacecraft passed within 18,000 kilometers of Antarctica, then turned its instrument deck toward home to capture images and spectra of the Earth and the Moon. The gravity assist bent the trajectory of Osiris-Rex by 6 degrees, matching the orbital tilt of Bennu and sending the spacecraft on a path to catch its target. In August 2018, Osiris-Rex began its approach phase. Its long-range camera captured the first visible light images of Bennu as a single pixel moving across a field of stars. Over the following months, Bennu grew from a pixel into a world, with Osiris-Rex revealing its shape, rotation, and color for the first time. Now, after chasing its target for over 2 years, Osiris-Rex is arriving at asteroid Bennu. On December 3rd, it will fire its thrusters to match Bennu's velocity and begin its preliminary survey. Osiris-Rex will pass high above the equator and the poles, measuring Bennu's position and mass, and refining its size, shape, and spin. On New Year's Eve, Osiris-Rex will venture close enough to Bennu to be captured into orbit by its minuscule gravity, making it the smallest world ever to be orbited by a spacecraft. In early 2019, Osiris-Rex will break orbit to conduct a detailed survey of Bennu. First, it will carry out a mapping campaign called the Baseball Diamond. By observing Bennu at different latitudes and times of day, Osiris-Rex will capture stereo images and identify large rocks on the surface that could pose a hazard later in the mission. In its second mapping campaign, Osiris-Rex will observe Bennu from 7 different stations around its equator. At each station, it will take measurements from pole to pole using its mapping camera, laser altimeter, and 2 spectrometers. The combined data will provide a detailed look at Bennu's geologic features and its composition. This will improve landmark-based navigation and enable mission planners to begin looking for places to collect a sample. Following the detailed survey, Osiris-Rex will once again enter orbit. At a radius of only 1 kilometer, Orbital B will serve as the mission's safe home orbit until sample collection. During this phase, Osiris-Rex will globally map Bennu. It will fly in a polar orbit as the asteroid rotates beneath, enabling full coverage of the surface. Orbital B's precession, or wobble, will also be used to measure Bennu's gravity field, along with the non-gravitational forces that are slowly altering Bennu's trajectory. In mid-2019, Osiris-Rex will begin its reconnaissance phase. It will break orbit and fly over 4 candidate sample sites at 225 meters, taking high-resolution images. Flying at such close proximity will reveal large pebbles that could pose a hazard during sample collection. Mission planners will use this information to select the 2 best sites for additional inspection. At a range of 525 meters, Osiris-Rex will fly over the 2 final candidate sites, spectrally mapping the surface to reveal its chemical composition. This information will help mission planners determine the most valuable site for collecting the sample. Once the final site has been selected, Osiris-Rex will begin its rehearsal phase. First, it will practice autonomous flight to a predetermined checkpoint, where it will start its descent during sample collection. Next, Osiris-Rex will practice flying to the match point. The spacecraft will lower to within 30 meters of the surface to match Bennu's speed and rotation, a necessity for safely touching the asteroid. Finally, in mid-2020, Osiris-Rex will be ready to collect a sample of Bennu. Before it descends to the surface, the spacecraft will deploy its touch-and-go sample acquisition mechanism, or TAG-SAM, a new technology invented for the mission. When it reaches the checkpoint, Osiris-Rex will begin its final descent. It will pull back its solar arrays for safety and approach the surface at centimeters per second, the walking pace of an insect. As the TAG-SAM touches down, it will blow high-pressure nitrogen gas into the soil, stirring up loose material. A filter within the sample head will trap rocks and dirt while allowing the gas to escape to space. Once the sample is collected, Osiris-Rex will fire its thrusters and back away from Bennu, retreating to a safe distance with its precious cargo. Following collection, Osiris-Rex will verify the status of the sample using a camera called SAMCAM. This visual inspection will reveal whether any large debris is still attached to the sample head, which could pose a hazard during stowage. Next, Osiris-Rex will verify the mass of the sample. It will fully extend its TAG-SAM arm and perform a spin maneuver, measuring the change in inertia to determine the sample's mass. If at least 60 grams have been collected and the sample head is clear of hazardous debris, mission planners will command the spacecraft to stow the sample. StowCam will watch closely as the sample head enters the return capsule and is secured in place. Osiris-Rex will then detach the TAG-SAM arm from the head, seal the sample return capsule, and prepare for its journey back to Earth. After departing from Bennu in early 2021, Osiris-Rex will return to Earth in late 2023. 4 hours prior to arrival, the spacecraft will release the sample return capsule, then deflect away from Earth to its final orbit as its piece of Bennu comes home. The capsule will enter the atmosphere over the night side of Earth, streaking towards the central California coastline at over 12 kilometers per second. West of the Great Salt Lake, at an altitude of approximately 33 kilometers, the capsule will initiate its parachute sequence, stabilizing and slowing its descent. Upon landing in the Utah desert, the sample will be recovered, carefully removed from the capsule, and taken to the Osiris-Rex Curation Facility at NASA's Johnson Space Center in Houston, Texas. This pristine material from the early solar system will be studied for decades to come, providing clues to the formation of the planets, to the evolution of Earth, and to the ingredients that were present at the origins of life.
Space Flight Center, and we are live here at Lockheed Martin in Littleton, Colorado for a truly historic event. In just a few moments from now, NASA's Osiris-Rex spacecraft is going to actually arrive at the asteroid Bennu. Now, it's been a 2-year journey to Bennu. The Osiris-Rex mission is something that's a wonderful collaboration between government, academic, and industry partners. The science team is led by the University of Arizona, and the mission is managed by NASA's Goddard Space Flight Center. And Lockheed Martin, where we are right now, built the spacecraft and also does operations for the mission. Now, there are a couple of really wonderful, unique things about this mission. This is actually going to be, as you can see here on this wall, there's some wonderful mission milestones here. It's going to be the first U.S. mission to return a sample from an asteroid. And in fact, this is going to be the largest sample return since the Apollo program brought back the moon rocks. So it's going to be a really significant sample. There's a new innovative technique of flying alongside the asteroid and basically just tagging it with a touch and go maneuver that will actually hopefully get 1 kilogram to up to 2 kilograms of material from the asteroid. We're also going to be mapping and studying this asteroid to incredible resolution. Think about this, 2-centimeter pixels. Bennu is about 0.5 kilometer across, the size of a mountain. We're going to be mapping this entirely new, unexplored area of the solar system. There also are some wonderful maneuvers. Bennu is going to be the smallest object ever orbited by a spacecraft. That means there are lots of maneuvers you need to do to orbit something that doesn't have very much gravity. So there are a lot of really innovative techniques that we're going to be doing with Osiris-Rex. So it's been a relatively long journey. As I mentioned, about 2 years to get out to this asteroid. So to give you a sense of a little bit of the mission timeline, Osiris-Rex was launched on September 8th, 2016. And one of the first things we did was we did a flyby of the Earth to boost us into the right orbit to encounter the asteroid. So you see that here. We were also able to test our cameras and take a wonderful picture of the Earth as well. Today we arrive at the asteroid, and we begin a 1.5-year program to scan and study the asteroid, eventually finding a location in the summer of 2020 to touch down and acquire the sample. The sample, once acquired, is going to be put into a canister, and it's actually going to be returned to Earth. You see here TagSam putting the sample into this canister, and then in the year 2023, September 24th, this will parachute through and actually land on the Utah desert. So what we're going to do now is actually go into the mission support area here at Lockheed Martin. Lockheed Martin is currently doing operations for 8 different missions, including the InSight mission, which you know successfully landed on Mars about a week ago. So we're going to be meeting some of the scientists and engineers here that are involved in this really, really exciting event. And we want to make sure that you're along with us too. So if you want to send us questions, there'll be a couple times during the broadcast that we can actually answer questions from our audience. Send the questions, use the hashtag AskNASA. Or if you're joining us on Facebook, put your questions down in the comments section, and we'll actually look for the questions there, and we'll get to as many of them as we can. So as a scientist, one of the things that I really have to say is that I am really, really excited to retrieve this sample from the asteroid Bennu. Asteroids are a remnant of the early solar system. About 4.5 billion years ago, when our solar system was forming, smaller objects were coming together to form the planets that we know today. And the wonderful thing about asteroids is that they are largely unaltered from this time. Rocks here on Earth have been melted, they've been modified, and they've been changed since they were first formed billions of years ago. With asteroids, you have a time capsule. You have a pristine sample of what the solar system was like billions of years ago. And that's why for scientists, this sample is going to be far more precious than even gold. So asteroids like Bennu are actually rich in organic molecules, carbon, the sort of chemistry that we're built out of. And there's even some suggestions that the water in the oceans of Earth, and even the water that's in your body right now, originally came from asteroids that impacted the Earth long ago. So as a scientist, this is a really exciting moment as we actually encounter the asteroid. So I'm here with Mark Fisher, and Mark Fisher is the chief spacecraft engineer here at Osiris-Rex. And Mark, tell me a bit about Lockheed Martin's involvement in this mission.
Well, welcome, Michelle. Yeah, we've been involved since the very beginning of this project. You know, how we have scientists and engineers getting together, trying to figure out what's possible to go get the best possible science. So Lockheed has helped in that design phase back and forth, what can we do? And then designed and built the spacecraft to accommodate all of those science requirements.
And we actually see some of the footage back here about the spacecraft actually being built and tested here.
That's exactly right. So right now they're going into an environments test where we simulate the environment of space in order to make sure that our spacecraft is going to perform as expected once we get it there.
So tell me a bit about what's happening today, just a few moments from now.
Yeah, so today is what we call arrival. So when we reach 20 kilometers from the asteroid, what we're going to do is do a burn to put us into the precision flying regime that we'll be doing for the next year and a half or so in order to map and discover all we can about Osiris-Rex and determine the best possible place to go get a sample of the asteroid and bring it back. So that's what we're doing today. It's a 28-second burn, 23 centimeters per second change in velocity.
It's really amazing. So, you know, I mean, after this burn now, Lockheed Martin goes into operations. So there's sort of a change in what you're going to be doing.
Right. So at launch, we actually make a transition. So we take some of very select people from our development team, because who best to fly the spacecraft rather than the people who designed and built it. And then we couple them with some of our operations people who really understand that part of it. And then we all work together. As you see, a lot of people here today work together to make all that come together and execute the mission.
Well, speaking of the people that are working together to execute the mission, there are many people at consoles here. Maybe you can take me through some of what's going on?
Sure, yeah. So like up here, we have the electrical power subsystem. So everything we do with the spacecraft requires power. We have solar panels and batteries, and they work in concert to allow us to maneuver around and do what we need to do as far as supplying the entire spacecraft with energy.
Absolutely.
Up here we have the thermal. He's trending and making sure that we're safe as we move around. Space is an environment for temperature. You get not only the cold that everyone's aware of, but also it gets very hot when you're actually in the sun. And so he's constantly having to balance all of those things to keep us safe.
That's something a lot of people don't think of. They think about the cold of space, but where the sun is hitting, you can get very, very hot as well.
That's right. And we want to optimize the spacecraft and the instruments to keep them in their proper temperature range so we get the best performance out of them.
So what have been some of the challenges? Oh, what are we looking at here?
Yeah, so here we've got the flight software, so that's kind of the brains in the spacecraft. We've got fault protection. All of our spacecraft are able to take care of themselves when they encounter a problem, and so they make themselves safe until they can contact the ground, or sometimes it just corrects the problem itself. As we move down here, we also see, for example, the systems group. Now, the systems group has a unique spot on this because they take all the information from the scientists, all the information from our navigators, all this subsystem information, and they put it all together to package up what we send to the spacecraft so it can go about its business and give us back what we want.
So when you look back on your involvement with the mission, what have been some of the challenges that really stand out to you?
Oh, yeah, so many challenges, but like one I would say in particular is the tag arm itself. So we had to have a way to land without landing an unknown environment. We didn't want to get caught trying to figure out how to land and then take off again. So this innovative technology that Lockheed developed, it's called the tag arm, and maybe if you've seen the graphics of it already, you have the asteroid and the tag arm comes up to it and it blows some gas and collects that in the sample. So we have testing that, designing that. How do you test that on the ground? We came up with innovative ways to use the airplanes the astronauts use to check that into low gravity.
That's right, so you'd have to actually test it in a microgravity environment because that's what the asteroid's going to be like.
That's right.
Well, thank you so much for talking to me. I'm really enjoying that. The next thing that we're going to be doing is we're going to be talking to the project manager, and here is Rich Burns, the project manager at NASA's Goddard Space Flight Center. So thank you for joining me today.
Thanks for having me, Michelle.
I'm going to hand you my microphone.
Very good, thank you.
So, Rich, maybe we could begin with sort of talking about the role of a project manager.
Well, the project manager is basically the person responsible for keeping the train on the tracks, foreseeing problems, making sure that resources are allocated to identify areas where we foresee risk.
And I think so the train on the tracks, so you're the person that's sort of in charge of making sure one thing leads to the next?
Yes, of course, and that job's really quite simple in this instance because we have such a wonderful team with all our partners are very highly capable, so it's a joy to be managing them.
It's an exciting day for you here, I imagine.
Absolutely. Arrival at Bennu is one of the key milestones in this mission, and we've been awaiting it for a very long time.
So just to remind you, you can actually take some questions live now. You can use the hashtag AskNASA, or if you're on Facebook, just put them in the comments and we'll get to as many questions as we can. So we're going to start with a question from David Watts from F22 Tech asks, what is the process involved in getting the spacecraft exactly to where it needs to be today and not shooting past Bennu?
That's a great question, David. In fact, in October, we were, in September actually, we were hurtling towards the asteroid. And in October, we executed a series of maneuvers to slow ourselves down. We call them the asteroid approach maneuvers, and they reduced the spacecraft speed relative to Bennu by over 1,000 miles per hour. These were large maneuvers we did with our main engines, and they're the last use of our main engines we'll have until we depart the asteroid. So everything from now on will be very small maneuvers to change our trajectory relative to the asteroid in very precise ways.
It really is incredible that this object is so small, and yet we're actually going to be able to go into orbit around it. That's very innovative.
Yes, and it's very challenging as well. The low gravity environment of Bennu is one of the foremost challenges associated with conducting this mission. Our navigation team is up to the challenge, and it has required some very detailed modeling of very small forces on the spacecraft. For example, the thermal emissions from the spacecraft as we rotate and change our orientation relative to the sun. The spacecraft will emit thermal energy that will change our trajectory very slightly, but that's important in this case.
That even leads into the next question. So the idea that the emission changes the trajectory very slightly is called the Yarkovsky Effect. And we actually have a question. So it's Lou Cipriano asks, will the eventual tag operation to collect the regolith material after Bennu's orbit, given the minute forces at play in the Yarkovsky Effect, it seems reasonable that the tag operation could have enough force to alter the orbit of the asteroid? Well, what would you say to that?
That's a great question, Lou. But our tag site is going to be so small relative to the overall size of the asteroid that we will not change the net effect of the Yarkovsky effect much. And let me talk a little bit about the Yarkovsky effect. I talk about thermal emissions from the spacecraft changing its trajectory, but also the same is true for Bennu. And Bennu is quite dark, so it absorbs thermal energy while the asteroid is in daylight. And as parts of the asteroid rotate into nighttime, they emit thermal energy, and it acts like a small propulsive force on the asteroid. As the asteroid rotates through night, it gets cooler, and that force gets smaller, and that's sort of asymmetry is the Yarkovsky effect, and it changes the orbit of Bennu over very long periods of time. Of course, it's a very minute force.
When you think about Osiris-Rex, it actually is an acronym. It's the origins, spectral interpretation, resource identification, security, regolith explorer, and so this is the security aspect of it. Is that right?
That's exactly right. As I mentioned, it changes the trajectory of the asteroid over very long periods of time. Bennu is a potentially hazardous asteroid. There's a very small chance that it will impact Earth in the next century. And the Yarkovsky effect is key in being able to predict Bennu's trajectory over that long span of time.
So we have another question. All right. So, Catalian on Twitter asks, is this the first time a probe has been able to send a sample back to Earth from another body?
Well, not exactly, but this is NASA's first asteroid sample return missions. Other probes have brought back samples. For example, Stardust brought back a sample of cometary dust. The Hayabusa mission from Japan brought back a small sample from its asteroid, but ours will be by far the largest sample collection from a robotic spacecraft.
I remember that you were telling me this was actually going to be the largest sample, but possibly up to 2 kilograms since the Apollo astronauts brought back moon rocks.
That's correct. It's very exciting. Yes.
Right.
And our science team is very eager to study this material that we'll get back from Bennu, which is thought to be the building blocks of the solar system. This is material that's been around since the birth of the solar system.
That's the origins part.
That's exactly
as the science goes. That's so exciting. Well, thank you so much for joining us. I really appreciate it.
Thanks, Michelle.
We are now, I'm going to grab the microphone from you there. We are now actually at 10 o'clock, which means that the orbit burn should really have happened somewhere out there in space. And of course, it's going to take the light about 7 minutes to actually get to us here. So this is, of course, a wonderful time. What we're going to do is we're going to go around and talk to some of the engineers that are involved in this process. And the first thing we're going to do is talk to somebody who actually does navigation. So once again, let me remind you that what you're doing right now is we are actually live at Lockheed Martin here in Littleton, Colorado, and we are about to arrive at the asteroid Bennu with NASA's Osiris-Rex mission. We're going to have another chance to answer questions later on in the program, so if you have any questions, use the hashtag AskNASA. Or if you're joining us on Facebook, please leave your questions in the comments and we'll get to as many of them as we can. So we're now going to talk about how you actually know where the spacecraft is and the process that goes into just doing these minute little operations to get it exactly where it needs to go. And the next person we're going to be talking to is named Coralie Adam. And Coralie Adam is a navigation engineer. So thank you, Coralie. It's great to be here with you today.
Great to have you.
This is an exciting time for you?
Yeah, really exciting. The burn just happened on the spacecraft, and we're waiting for the signal to come back in a few minutes here.
So tell me a bit about your job as a navigation engineer.
So I work on the optical navigation component of the navigation system. So to navigate to Bennu, we have to determine the trajectory of the spacecraft that is flying currently. We plan its future trajectories, and we design the maneuvers to get us on those trajectories. And in order to determine where the spacecraft is, we use two types of information. We use the optical images that the spacecraft takes of the asteroid, and then we also use the signal from the spacecraft in the communication link when it transmits things down to Earth.
So when you talk about optical communications, I mean, optical navigation, there's no GPS in space. It's very hard to tell exactly where you are. You actually use the background stars to navigate and tell you exactly where the spacecraft is. Is that right?
Yeah, we use the background stars as the reference frame to tell us where the spacecraft was pointed when it took the picture. And then we can use where we observe Bennu in the picture relative to that to figure out where the spacecraft was relative to Bennu when it was taken.
So can you tell me a bit about what you're looking at here on your screen?
Yeah, so this is the trajectory that we're about to fly. So we just are doing M1P, the first maneuver of our preliminary survey mission phase, where we're about to do our first close flyby of Bennu, less than 5 miles, which will be tomorrow, 24 hours from now. And so we are going to do that 3 times. We're going to go over the North Pole 3 times, and then we're going to fly over the equator and the South Pole. And that allows us to not only estimate the gravity, the mass of Bennu for the first time, which will help us design our future orbits downstream, but it also allows us to map the whole surface and build landmarks that we're going to use to navigate once we get into orbit.
It's sort of amazing. So you're actually going from using things like stars and signals from the spacecraft to navigate to knowing Bennu well enough that you can actually sort of navigate by local landmarks.
Right, absolutely. Yeah, we're building these maps, and that will give us the precision that we need to continue on to higher mapping phases and lower orbits. It will really be record-breaking in terms of the precision navigation that we've done in space before.
It's an exciting moment. How are you feeling?
I'm nervous and excited.
Have you done this before? Is this sort of the first time this happened with you?
I got to participate in the Pluto mission, so that was my first mission, and this is a totally different type of mission, though. It's really like flying a different mission every phase. We're doing all sorts of different orbits and science for the next 2 years. So this is really day 1 of proximity operations at Bennu.
Well, thank you so much for talking to us. I'm really excited too. So now we're going to go over and we're going to meet Javi Serna. And Javi Serna is our telecom systems engineer. So Javi changed right over there. There we go. There, Javi's right here. I'm getting so excited. How you doing, Javi?
I'm doing great. How about yourself?
I'm doing very well. Okay, so tell me a bit about what you're doing right now.
So right now what I'm doing is I'm actually monitoring the transmitted signal from the Osiris-Rex spacecraft. So what's happening is the DSN has transmitted a radio signal to the spacecraft. The spacecraft has then taken that signal, turned it back around, and it's received here on Earth. And what I'm looking at is a real-time measurement of that signal. And that gives us 2 things. It gives us a quick access into how well the comm system is performing, but additionally it also provides us with Doppler, which is the change in velocity of the spacecraft, which is crucial information that the navigation team uses to essentially assess how things are happening as we about to approach the burn.
Now you mentioned something called the DSN. That's the Deep Space Network.
The Deep Space Network. So it's a series of events kind of scattered, a series of antennas all across the Earth. And so basically we use those antennas to basically lock into the spacecraft and then receive the signal from the spacecraft back.
So what we're going to be looking for now, or very soon, is going to be a change in velocity.
A change in velocity, and you can see here I have the Doppler residual up, and so we're basically, as soon as the burn, we receive the signal here on Earth, we'll see a Doppler shift, which should tell us that the burn has started.
So how long have you been working here at Lockheed Martin?
I've been working here about 8 years and about 7.5 with the Deep Space Exploration Division.
So how are you feeling right now?
A little nervous. After this burn is completed, we're going to be approximately 7 kilometers away from Bennu at the closest approach. So it's exciting, a little intimidating. There's a lot of feelings going through me right now.
What are some of the things that you're going to do after this event? So when we go into proximity operations, does your job change a bit?
A lot of it stays the same, so it's kind of working in concert with navigation and kind of assess when Doppler is available, when ranging is available. Ranging is a measure of distance to the spacecraft, so we work closely with them to essentially keep providing that information to them so they can ultimately continue to build the ODs.
So how much time do we have now?
It looks like we have about 40 seconds or so before we start seeing the actual burn. And some other things that I look at is I'm looking at this graphics page, which kind of just quickly assessing the health and status of the components. So our transmitter and then our amplifier.
So just to remind you that we're live here at Lockheed Martin, and we are just about to arrive at the asteroid Bennu and begin proximity operations to study this asteroid, eventually returning a sample back to Earth.
Yeah, it's so exciting. I can't believe we're here. We're right there. All stations, stand by. Burn has started. Stand by for Bennu arrival. So you can see here we have the Doppler residual, so we know the burn is occurring because I'm seeing a change in velocity from the spacecraft.
It's gotten very quiet in here. Everyone's whispering.
We have arrived.
You may have noticed we were doing a bit of an unusual high five there. That's called the tag five, because that's reminiscent of the tag SAM arm that's eventually going to retrieve a sample. So we're just going to sort of watch people enjoy themselves. We have arrived at the asteroid Bennu. The spacecraft has successfully done the engine burn to put us into proximity operations at this asteroid. The light travel time to the asteroid is currently about 7 minutes, which means the asteroid is somewhere on the order of, probably the high 80 million miles away. So it took us about 7 minutes to get the signal to confirm that we have in fact arrived at Bennu. So now I'm standing here with Heather Enos, and Heather is the deputy principal investigator of the mission from the University of Arizona. So, okay, Heather, what are you feeling right now?
My heart rate is like 3 times faster than normal, but I'm super excited. I mean, watching the team celebrate such an amazing milestone honestly brings personal joy to me in so many ways I can't even explain. These guys are, and women, such an amazing team, and I'm so proud to be part of it.
I think a lot of people don't realize the amount of time needed to make a mission like this. How long have you been working on Osiris-Rex?
So I've been working on this mission for nearly a decade. I started working on it in 2008, and that was the beginning of the design of the mission. And bringing together this amazing team to go through development and then eventually operations, launching in September 2016. And although today's our arrival, we've been doing a lot of things since we launched and during our approach, exercising the team, our instruments, our spacecraft. So it's been a long time coming to the arrival, and we're really looking forward to the next chapter of this mission.
I always love moments like this. People think of science as being kind of dispassionate, logical, not very emotional, but you can sort of see the tension on people's faces, and then there's sort of this joy that erupts.
Yeah, no, I'm probably one of the more emotional ones on the team because I take, it's a family, it's not just a team. And watching everybody grow every day really is very satisfying.
Okay. Right. Well, after that moment, we have a chance to actually talk a little bit about what's going on in your role in the mission. So, as the first thing that they're going to be doing is actually rolling a video, I believe, of images of Bennu as Osiris-Rex comes up. So, what are we looking at in this video?
So, during our approach, we've been slowly creeping up to Bennu, and during that time, we've been taking the opportunity to snap images using the OCAM's camera suite that was built at the University of Arizona. So we've had a very active campaign imaging Bennu as we're approaching the surface. And it's given us an opportunity to really get a sneak peek at what we're about to embark on. So we're getting great images back. We can see the surface has got a lot of boulders, craters, a lot of diversity in the surface. So it's been really exciting.
So talk a bit about your role. So you are the Deputy Principal Investigator. What is your role in the mission then?
So as the Deputy Principal Investigator at the University of Arizona, Osiris-Rex is a Principal Investigator-led mission out of the University of Arizona. And so what that means is we have the overall responsibility of ensuring that we meet all of our science requirements that we have agreed to with NASA, our stakeholder, and our partners, in addition to making sure that we stay within our resources that we've agreed to. My primary role during operations is to oversee the Science Planning and Operations Center as we're doing operations implementation, as well as we have the Science Processing Center at the University of Arizona. So I oversee that on a pretty daily basis. I work really closely with our team to make sure we have our plans in place and that we have all of the people and resources necessary to get our jobs done.
Well, let's get to a couple questions people are actually sending in. So let's see, we have a question for Heather. Marcia Dunn from AP asks, also when the spacecraft was launched, Bennu was described as a roundish black asteroid about 1,600 feet at its middle. Any updates, please, on your description of the asteroid now that you're up close and personal to it?
Yeah, so Bennu is a very exciting small body, and our science team did a really great job characterizing the asteroid prior to us selecting it. Bennu is considered one of the most characterized asteroids that we have. However, the data that we are collecting is really very indicative that the science team was very good at doing many good predictions in terms of its mass, its size, its albedo. And so we're getting confirmation that a lot of the assumptions were pretty close to accurate, but we also are getting images that we've never seen before that are giving us a lot of insight to potential sample sites that we will start to explore more thoroughly over the next year and a half.
So when are we going to hear more about the sort of preliminary science results that are coming out?
So the science team is working really hard, as well as the implementation team, to get the data necessary to go to the next step. But we are planning to unveil quite a bit of our preliminary results at a press media event that's happening at AGU on December 10th at 2 p.m. Eastern. And so that'll give an opportunity to start to unveil many more images, our shape model, and hopefully.
Over 200 meters away from the International Space Station. A very slow approach at this point at about 0.3 meters per second.